water takes that proton, it gives H3O, which has a 0, so pKa. By definition, it's 0, right?
Yeah.
So they're within the same range. They're within the same range, so it's definitely very equilibrium. So that's the mechanism. Remember it. But what I really do want to say is, we'll get back to that in the future. But I really want you guys to remember, unlike any of the other electrolytic substitutions I've mentioned, sulfonylations we can take off easily. Whereas other things we need more modern chemistry. But sulfonylations, as far as this class is concerned, are the one reversible one. So in chapter 15, we can put on sulfonyl groups, sulfonic acids, and we can take them off. So that's the key message from that. We can put them on, and we can take them off, and that's a useful thing to know. And I'll explain why. So now, let's talk about the two final reactions we're going to talk about in chapter 15. And that is the Friedel-Crafts alkylation and the Friedel-Crafts acylation. And Friedel and Crafts were just German chemists from a long time ago who discovered the reaction. So Friedel-Crafts alkylation. And because I'm not very good at spelling German names, I'm just going to F.C. Alkylation. And acylation. So the alkylation is you take your aromatic group and you take an alkyl halide. So an RX. Particularly, you want your alkyl group to be an sp3. So really, it's going to be sp3 carbon methylene unit. And we usually do chlorines or bromines, but for this sense, let's just go chlorides. Someone have a question? All right. So, I think someone said bless you, I apologize. So someone said RCl, and then you use Lewis acid. Lewis acid we use for this is aluminum trichloride. So it's AlCl3. And the product we get out will be the alkylated product. So the way we put on an alkyl group is we take our sp3 alkyl chloride and AlCl3. And then the aromatic system is going to attack this, giving us our cationic intermediate, and it's going to collapse. And I'll show you that in a second. So the first part of the mechanism, as always, is going to be your electrophilic activation. So E for electrophile activation. And what I can tell you is the mechanism really depends on whether or not you have a primary, a secondary, or a tertiary alkyl chloride. And basically, if you have a secondary or a secondary or tertiary, it's going to be a lot like an SN1 reaction. If you have a primary, it's going to be a lot like an SN2 reaction. So let me do the primary first, and then I'll do the other two. We're out of space. So for this one, what happens is the lone pair of electrons from the alkyl chloride is going to attack the AlCl3 and that'll give us this kind of species, which is very similar to what we saw in the halogenation case. In fact, because of that, the halogenation I showed you with the FeCl3, a lot of people call it a Friedel-Crafts halogenation because it's the same thing, the lone pair of electrons from the halogen attacking the Lewis acid. So very similar to that. So in this case, this can easily fall off to give us a primary carbocation. But what's the problem with primary carbocations? They SUCK. I've got to practice being a dad's art to make sure I don't say these, words out loud. So yes, a primary cation is not that stable. So the chemistry will go through this in an SN2 reaction. Just to show you. The benzene ring will attack the activated electrophile, kicking F to Cl, giving us our cationic intermediate. Like so. So then the electrophilic attack is the same to everything we've shown, right? It attacks in an almost like an SN2 type fashion, giving us our cationic intermediate. Then we form, of course, in this step, we form AlCl4 minus. And the AlCl4 minus is going to act as our base. So let's go AlCl3 with the fourth chlorine sticking out. It's going to act as the base, regenerating the aromaticity, giving us a product. So again, the mechanism isn't that different at all from anything we've seen, right? We activate the electrophile by the halide attacking the Lewis acid, giving us this activated sp3 alkyl chloride, where there's a positive charge in the chlorine, but we know from electronegativity the positive charge isn't going to lie in the electronegative chlorine. It's going to lie in the electronegative carbon. So lots of partial positive charge here, more than before. And so now since it's so activated from this, it's going to attack, the aromatic pi system's going to attack. They give us our, electrophilic aromatic substitution carbocationic intermediate, and then the generated Lewis base, AlCl4 minus, is going to grab the proton to regenerate it. So again, the only new stuff here is how we activate the electrophile with Lewis acid. Everything else is the typical classic tried and true electrophilic aromatic substitution mechanism. Now, can the camera see this? Or should I move this over? All right.
The aluminum should have a negative charge, right?
Yeah, there's not a negative. You mean there's minus charge right here? Huh? Oh, you mean, oh. All right. Rain gel. That's what that was, a rain gel. Thank you. So I'm going to slide this. Oh, whoops, I guess I can't slide this. So, with with primary sp3s, it's not, again, with primary sp3 chlorides, it's going to go through an SN2 mechanism. If we have secondary or primary, secondary or tertiary alkyl halides, it's going to go through an SN1. And so what's going to happen is the chlorine, if we have a secondary or tertiary, is going to attack the AlCl3, giving us, again, that same weird intermediate with a positive charge in the chlorine and a minus charge in the aluminum, like so. But now, in this case, since we have a secondary or possibly a tertiary carbocation, now we can actually form the carbocation. To give us, in this case, our secondary carbocation plus AlCl4 minus. Then, for this case, it becomes really easy, the same mechanism. So once we do this AlCl3 to form our carbocation, we can throw into our aromatic system. And the aromatic system will attack through electrophilic mechanism, through electrophilic aromatic mechanism, the carbocation. All right, again, giving us our cationic intermediate. And now, as always, our AlCl4 minus, or FeCl4 minus, is going to act as a base and grab the proton. To give us our alkylated product. So, with these conditions, when you have a secondary or tertiary, it's just going to be an SN2 type mechanism. So SN1 type mechanism, where the aromatic system attacks the carbocation. And this is the best case scenario for a Friedel-Crafts alkylation. You really want it to go to the carbocation. You really want it to go to the carbocation. And this brings up one more point. When you have a secondary or tertiary system, you don't need to use AlCl3. Well, you can, but you can use any way we've talked about in this class to generate carbocations. Any way to generate carbocations we've talked about in this class you can use. Someone give me a way to make a carbocation.
LAH?
LAH is a nucleophile, so that would not give a... so, how radical, could possibly do this, but slightly different. What kind of reactions have we talked about a lot that generate a carbocation intermediate? What? Br2, that's the right track. But what do we react Br2 with? An alkene, right? So in 232 a lot, and in chapter 13 a lot, we generated carbocationic intermediates from adding some kind of Lewis acid, or acid itself, across the double bond. That's a great way to form carbocations. So just to give you a classic example, you can get an electrophilic aromatic system, electrophilic aromatic substitution, Friedel-Crafts alkylation, by taking an olefin, taking an alkene, and H2SO4. And when you take an alkene and H2SO4, what's going to happen, of course, the double bond, the alkene's going to become protonated, because we know this is the first step of adding water across an olefin using acid. So this will give us our most stable carbocation, which is going to be the proton coming off here. And our tertiary now carbocation, which is pretty darn stable, relatively. And now, we form a carbocation. We do our EAS, so the attack to get the carbocation intermediate, and then the rapid E1 elimination to give us the product. I won't draw it out because I've drawn it out 5 or 6 times today, and the mechanism's the same. And so then it will put our carbon with 3 methyl groups on our benzene ring. So you can do a Friedel-Crafts alkylation with a secondary and tertiary olefin just as long, so secondary or tertiary carbocation, you just need to form the carbocation in any way possible. And so remember from Chem 232, alkene plus sulfuric acid is a great way to generate a carbocation. And if you do it in the presence of a very strong aromatic system, the aromatic system is going to intercept the carbocation. Yeah?
The H1SO4 is strong enough base to grab the...
Only because we're generating aromaticity. Only because the product's going to be aromatic. So the fact we're regenerating aromaticity is going to be what's pushing that reaction forward. Right? Because HSO4 is a pretty lousy base because its conjugate acid is sulfuric acid. So, the Friedel-Crafts alkylation is very nice, and it works great. But there's one issue. What is an issue when you're dealing with what do you worry about when you're dealing with carbocations? That you guys talked about, I know, in 232. Rearrangements, exactly. Rearrangements are a pain in the butt with phenol-Krauss alkylations. And so in general, just a little philosophical thing, if you generate something with high carbocationic character that can rearrange to give a more stable carbocation, it will. Because that's what carbocations do. They rearrange until there's the most stable carbocation. So, to show you, I'm going to get rid of this now. Let's say, hypothetically, you wanted to make let's say you hypothetically wanted to make this. Let's say this was an intermediate towards the cure to diabetes. Or maybe not a cure, a very good treatment for diabetes. This would allow your grandma to eat cookies again. Right, so this is a very important drug. And by the way, most chemists that stay being chemists and get jobs, a large percentage of them get jobs in the pharmaceutical industry doing just that. Figuring out ways to make and improve small molecule therapeutics for the betterment of life. So that's a big aspect of what chemists do, is work towards making better pharmaceuticals to treat disease. Big part. So let's say we wanted to make this. How would we? Well, the first approximation you'd say, well, let's just do a phenol-Krauss alkylation. And so the retrosynthesis would be, let's start off with benzene. Plus this alkyl chloride. Here's the problem why this wouldn't work. If we did this reaction, this plus this, and AlCl3, the product we would get out would actually be this product. So instead of having two methyls and a methylene, we rearrange so we get a cation that gives this. So what is happening is this is going to attack the AlCl3 on the metallic intermediate over here in green. So the first step is going to be the same. But now what can happen is, so we have a lot of partial positive charge at this carbon. So there's a lot of cationic character of this carbon, but it's primary, so it's not going to fully commit to give us the carbocation. But what we can do is we can have a 1,2 hydride shift, so a hydride rearrangement. And so if we do this hydride rearrangement, so here's our chlorine, activated chlorine carbon sigma bond, and it's fairly overlapping with this carbon hydrogen sigma bond. And so when you have orbitals overlapping with a bond, you can definitely do a shift. Yes?
The dash line on the far of
This
that
one?
formula? Yeah, is that a methyl?
Methyl, yeah, methyl. If you can't read the scribble, it's probably methyl. That's just not my curse, that's most chemists' curse. So what's going to happen is this carbon hydrogen bond is going to jump into this empty bonding orbital of the activated chlorine carbon sigma star bond, kicking off the activated thing. From this hydride shifting, that's going to give us our tertiary carbocation plus AlCl4. And we'll get this product. So, if we really do need to make this, how do we do it? The answer is not via a phenol-Krauss alkylation. The answer is via a phenol-Krauss acylation. And so now that leaves me, so remember this thing. With phenol-Krauss alkylations, because you form carbocations, rearrangements make things difficult, so be aware. With the phenol-Krauss alkylation, rearrangements will and can happen. So whenever you're doing a Friedel-Crafts mechanism, whether it be in an exam or anywhere, just realize when you form your activated intermediate, ask yourself, can this be arranged to give me a more stable carbocation, either through a carbon or a hydrogen shift? Because if it can, it will. It will. So now let's time for a Friedel-Crafts acylation. And so I'll just keep the little heading, that it still fits. And so now this is going to be the Friedel-Crafts acylation. And so in the Friedel-Crafts acylation, let me grab the black one. We take an acid chloride. We won't learn the Lionel acid chlorides until chapter 17 or 16. Just realize acid chlorides are very electrophilic carbonyls that have a very good chlorine leaving group. Chlorine is a great leaving group because it's got a good acid as HCl, so it's a very stable anion. So chlorine is always a great leaving group. And so when you take an acid chloride, and again, AlCl3, what we will get will be an acylation. Where we just made a carbon in our aromatics, so our aromatic system just made a bond between one of its carbons and now the carbon of a carbonyl. So we just made a ketone. We just made a ketone, an aryl ketone. And so the mechanism of Friedel-Crafts acylation is very similar to things we've seen. So first step, the lone pair of electrons on the chlorine are going to do what? Attack the AlCl3. And that's going to give us the same intermediate, which we've seen things a million times before, right? Today at least. So we form this anionic aluminum and this positive charged chlorine. Now the major thing that's changed, that's different between the alkylation and the acylation, is that in this case, this oxygen has lone pair of electrons on it, right? What do you think these lone pair of electrons are going to do? E2 type elimination. So these lone pairs of electrons are going to kick down here, breaking this bond, giving us this really high energy, freaky looking intermediate. So we form this, and then we have AlCl4 minus. This is an activated electrophile, right? This just does not look stable. This looks like a super, super electrophilic carbonyl, and it is. This is like the most reactive carbon-oxygen bond you can get for electrophilicity. So then what happens once you form this, your